Hello and welcome. Today the topic is all about interrupts. We're going to talk about how interrupts arise, how they propagate through the peripheral interface adapter, how they then actually interrupt the CPU, what the CPU does, how you set them up, how you handle them, and all that good stuff. We'll also be focusing specifically on the vertical sync or field sync interrupt, what that is, what it's all about, and how you would handle that. Your 6809 CPU is going along, minding its own business, executing instruction after instruction. But as you may know, the very next instruction after this one might be this one, or it might be something completely different and far away. And that depends on whether the CPU has been interrupted. This is a picture of the CPU, the 6809, with all of the different pins. And as you'll see, some pins are dedicated to implementing interrupts. So you have your NMI, your IRQ, your FIRQ, and your reset. When a signal comes in, that's the CPU's hint that it needs to stop whatever it's doing, interrupt it, and go and run an errand first, and then come back. Most of these I'm not going to talk too much about. The reset pin, I don't even know if you can really call that an interrupt, although it does technically interrupt whatever the CPU is going to do. And that's used with powering on and the reset button on the Coco. Software interrupts are instructions, opcodes you can put into your code stream to interrupt yourself from whatever you were doing to do something else. Not going to talk too much about those. The non-maskable interrupt is an interrupt that you cannot stop using the condition codes register. It's tied to pin 4 on the cartridge port, and DiskBasic uses it to help with copying bytes to and from the disk to break out of loops. I'm not going to talk too much about that one either. We are going to spend most of the time talking about the peripheral interface adapter interrupts. These are the hardware interrupts that go through the peripheral interface adapter chip. And that looks a little something like this. So you have a piece of hardware, maybe it's the video display generator, maybe it's your serial port. And it's like, I want to interrupt the CPU, but it's not my friend, and I don't want to make it mad. So I'm going to talk to my best buddy, the peripheral interface adapter. Hey, Pia, would you mind interrupting the CPU for me? I know you got a direct line on him. And Pia says, I'll try, but I got to make sure I was programmed to do it. And if it was, the Pia goes ahead and sends a signal on one of those pins, either the IRQ or the FIRQ on the 6809, and interrupts it. There are actually two Pias on the Coco. The first Pia is connected to the video display generator, and it's capable of a couple interrupts coming from it, and those interrupts go through the IRQ. The second Pia is connected to the serial I/O port and also pin 8 on the ROM cartridge slot, and those interrupts go through the FIRQ pin. The behavior of the IRQ and the FIRQ are pretty much the same. The main difference is that the system will save all the registers for you when an IRQ is signaled. With an FIRQ, it's up to you to save whatever registers you use. So this F stands for fast. It's faster because it's not saving everything. And just for completeness, pin 4, as I mentioned, goes through the NMI pin directly on the CPU. So no PIA is involved with that. I'm going to be focusing on the PIA 1 because the interrupt generated by the VDG tends to be one of the most useful interrupts. In particular, this one right here. This is how the VDG draws to the screen. It has a border at the top. It's got borders on the left and the right. It's got a border on the bottom. And then it has the active display area that we're all used to drawing in. All of that accounts for the visible area, but there is an invisible area. What is that? Inside this CRT TV is an electron gun. It shoots a beam of electrons from the back of the TV to the screen. And the screen is coded. Whoa, there's a gun that shoots a beam of electrons in my TV? Yeah, that's bananas. Pretty wild. Like some crazy Star Wars stuff right there. Actually, the technology is about 100 years old. What? Yeah, it wasn't in homes until like the 50s, but the technology existed decades before that. That's bananas. Pretty wild. Is it okay if I get back? Oh, sure, yeah. So there are phosphors on the screen that glow when the electrons hit them, and that's the light that you see. So as the gun moves across the screen, it's following a signal that's transmitted to it. And as the signal grows in intensity, the electrons grow in intensity, the amount, and then that will glow even brighter. So there's like a continuous signal that goes across as it moves that makes it darker, brighter, darker, brighter, darker, brighter. And then it rewinds back and goes to the next line and it does the same thing there, but with slightly different signal for that next line, and so on, and it keeps doing that. With NTSC, which is interlaced, it will do first all the odd lines, and then it'll rewind back up to the top and then do all the even lines, and then it can do like a full frame worth 30 times a second, which means all the odds or all the evens are happening 60 times a second. Now, as fast as it's moving, there is still a limit to how fast that electromagnetic field can move the beam. So by the time it gets to the end of a line, it can't come back here instantaneously. There is some amount of time that it takes for it to come back. And that time was built into the signal. It's called a blanking interval. So from this point forward, there is no new picture data coming in until the TV has time to rewind that beam to the left. The same thing happens by the time it gets down to the bottom. It has to then rewind back up to the top to begin the lines of the next field. And that time is called the vertical blanking interval. In fact, they kind of figured out that during that vertical blanking interval, the TV does not need to rely on a signal to tell it to turn black. The TV can just know to go black, and in that time, the signal can include other non-picture information, such as closed captioning or station identification, or just meta information about the program. So the field sync interrupt is the thing that we're going to be most interested in. The falling edge of that signal happens right after the active area on the bottom line. And that signal remains low as it goes through all the retracing and through most of the blanking, and then it goes high. So your interrupt handler has all of that time to do whatever it needs to do. But just because the VDG is capable of issuing that interrupt does not mean that interrupt is going to happen. You need a perfect storm for an interrupt to actually interrupt the CPU and go to an interrupt handler. First, you've got to have an interrupt signal. We talked about that. Second, you've got to program the PIA. You have to enable the interrupt. And that's why in this diagram, I mentioned that the PIA would happily do the hardware's bidding, but only if the PIA has been programmed to do so. Otherwise, the interrupt never goes further than this. And finally, the condition code register has to not be masking that interrupt. Not only does the PIA have to be enabled, the condition code register has to not be disabled. Let's dive into the detail of these two. This handy dandy chart shows you the two PIAs and what you need to access to program them. This is our VDG PIA. It's the one that issues the IRQ. And this is where the vector handler starts. There are 3 bytes in RAM starting here that form a jump instruction. So when an IRQ occurs, the CPU goes here and executes whatever is here. And that helps it to jump to the handler. You have a choice when you're writing to this memory location. You can take stock of the vectored handler that was there before, and then choose to call it from your vectored handler so that everyone gets a chance to play the game. If so, you're going to need to store that somewhere and then have an instruction in your vectored handler that jumps to it when you're done. Or you could make believe you're the only person in the universe and not call that vectored handler. Just completely overwrite that jump with your own location and only do your thing. The choice is yours. There are 2 halves to the PIA1. The CA1 handles the horizontal sync interrupt. And that happens for every line, so this is very frequent and needs to be very fast. This is not as useful. The CB1 half issues the field sync interrupt, and this is what lots of folks use. Notice that they share the same vector handler. So if you really want to use both, your handler has to be able to deal with being called for both. And that leaves these. So you program the PIA by talking to the control register and the data register. And each half of each PIA has a different dedicated address for the control register and the data register. What do they look like, and what do you do to them? So here's a breakdown of the bits in the PIA control register. Think about this like an alarm clock. So bit 0 decides whether the alarm clock is set or not. If it's 0, the alarm clock's not going to fire, there won't be any interrupts. If it's 1, then it will fire and there will be interrupts. And that was a little bit of a lie, I'll get back to that in a second. Bit 1 decides when the alarm clock goes off. So each interrupt has both a falling edge and a rising edge to its signal. If you're doing, say, a vertical sync or field sync interrupt, the falling edge happens earlier, and it happens right as we go from the visible area of the screen to the invisible area. So by responding to this one, you get more time to do what you need to do before the next frame starts. So this is a better thing to respond to in most situations. Bit 2 is insane. I'm going to get back to that in a second. Bit 7 tells whether the alarm should be currently alerting you or not. If it's 1, that means that the hardware has just asked the PIA to wake up the CPU and interrupt it. The interesting thing is this will be 1 even if the alarm clock is turned off. So even if you chose to disable, this bit will still tell you whether an interrupt should be happening. But an interrupt will not be happening if this is off. What's important to know about this is you have to acknowledge this by turning it off. This is kind of like hitting the button on the alarm clock when it fires and you wake up and you got to turn it off. This doesn't turn off future alerts. This just turns off the current alert. In a little bit, I'm going to show you some code of what happens when you fail to turn this off and the wild antics that will ensue. Now you may be thinking, okay, I turn this off by ANDing a 0 in here, just like I would fiddle these bits by ORing or ANDing 0s or 1s over here. But no, you can't do that. Instead, you have to read from the data register to write a 0 here. As you may recall, each half of each PIA has its own control register and data register. So while all those writes are happening, say, at FFO3 for the field sync interrupt, you have to read from FFO2 in order to write a 0 into bit 7 of this. And even that is not convoluted enough. That brings me to bit 2 over here. As it turns out, each address for each data register is also an address for something called the data direction register. So if I were to read from FF02, I might be reading from the data register, or I might be reading from the data direction register. This bit determines which register that address is mapped to. Since we're not going to be using the data direction register, you need to make sure this bit is 1, so that every time you do this read, you will actually be doing a write of a 0 over here. Oh my gosh! Again, I'm going to show you some code that does all of this. Hopefully it'll make a little bit more sense when you see that code. Now, as I mentioned before, these two things have to be true for an IRQ or FIRQ to go through. So we talked about enabling the PIA. We also have to ensure that the condition code register doesn't mask that interrupt. Here's your condition code register with a lot of the typical well-known bits like the 0 and the negative and the overflow. But it also has the FERC and the ERC. If these bits are 1, the interrupt is masked, which means it's disabled. So if the CC is on, the interrupt is off. All right, let's put this together. We'll talk about how to set up an interrupt, and then we'll talk about what your interrupt handler needs to do. The first thing you're going to want to do is to mask the IRQ and FIRQ while you do your setup. This will put a 1 in the FERC and the ERC bits. And now you don't have to worry about an interrupt happening while you're doing your setup. Next, you need to go to that vector and write your address. For example, you would go to O10C, skip over that byte, which is just the jump instruction. And then the next 2 bytes, you would put your address where your vectored handler will be. Next, you program your PIA. So you write to the control register, and then you do that final read of the data register to get it all enabled and ready to go. At this point, the PIA will start propagating interrupts to the 6809, but the 6809 will ignore them because the condition code register has not been reset yet. Which brings us to step 4, clear whichever of those flags you care about handling. So if you're writing a FERC, clear the F. If you're handling an ERC, clear the I. If you want them both, clear them both. Here's some example code to do all of that stuff, and a little later we're going to run this so we can see it in action. All of the code you see here is either identical to or was at least started from the code on nowhereman999 wordpress.com, awesome blog. I'll put a link in the description. I highly recommend you go there and read up on that stuff if you want more info. So the first thing we do is we mask the interrupts. So we're putting a 1 in the I and the F bits of the condition code register. So there shall be no FERC and no ERC, at least for the duration of this initialization routine. I am disabling hsync. This is probably not strictly necessary because it's already disabled for me by BASIC. But just so you can see what it looks like, we go into the control register for that side of the PIA, FF01, and we turn off the alarm clock. And now that we've taken the control register and just zeroed out the 0th bit, we stick it back into the control register, and that's it. That's all I'm going to do with hsync. For field sync, our control register is FF03. We load that in. And now we're going to set bit 0 and 2. So setting bit 0 turns on the alarm clock, and setting bit 2 allows any reads we do from FF02 to go to the data register. So these are the 2 ones we need to set. We also need to AND in a 0 in bit 1 so that the interrupt happens on the falling edge of the signal. We put that new value back into the control register, and now I can do a load A into this address for the data register, and that will flip bit 7 of the control register to be 0. You'll notice I'm not going to do anything with this A that I loaded. You could load any A or B, it just doesn't matter. All that matters is you kind of tickle it by reading it, and then that causes a 0 to be set in bit 7 of the control register. It's crazy! Now at this point, the PIA is going to be receiving interrupt requests from the VDG, and it's going to be setting this bit 7, potentially, if an interrupt comes in right now. But it won't cause the CPU to be interrupted because I do still have the condition code register masked. So my final task is writing the address of my interrupt handler into 010C. In particular, I stick a jump instruction at 010C, and then I put the address of my handler in the next 2 bytes. And my handler, we're going to see this a little bit later. It's just right here. That's just the label for it. You'll notice that I'm being king of the universe here. I'm not taking a look at whatever handler used to be here and chaining to it. I'm going to be the master of the universe, and I'm the only one who exists, and mine is the only handler to run. And finally, we unmask the interrupts. That's a double negative. Masking would mean we would have a 1, and that would disable. Unmasking means we stick in the 0, so it is enabled. And you'll see I'm just unmasking the I bit. The F bit, the FERC bit, I'm leaving that as 1. I'm leaving it as masked because I still don't want any FERCs anyway. And that's it. So I just call that from the very beginning of my main loop, and that sets it all up. Finally, what are your responsibilities in the interrupt handler itself? Well, first of all, if you're handling a FERC, you're going to need to save whatever registers you use, so be sure to do that. Next, presumably, you are writing a handler to do a thing. So do that thing, whatever it is. And now it's time to get out of there, so you have a choice. If you've been chaining interrupt handlers, jump back to that original vectored handler that was written in the jump instruction before you came along. And it should handle all of the cleanup for you. But if you're taking over and you have complete control and there is no other vectored handler you're chaining back to, you got to clean up yourself. That means reading from the data register to acknowledge the interrupt so it doesn't keep on hammering the CPU. If this is a FERC, this is your opportunity to restore the registers that you saved. And finally, do your RTI. Now you may have noticed I didn't talk anything about the condition code register with respect to your interrupt handler, and that's because you don't need to do anything with it. The CPU will automatically mask the FERC and the ERC flags for you. This happens as soon as the interrupt begins, before your handler is even started. And once you're done, the CPU will automatically unmask them just by virtue of having restored the CC register from before it tampered with it right when the interrupt came in. The first thing I do is a little odd. These two lines, I'm taking a look at bit 7 of the control register. So bit 7 would determine if a value is positive or negative. So if it is set, this is going to be negative. And if it's 0, it's going to be positive. I want it to be set. I expect it to be set because that would indicate that I'm looking at an interrupt from the vsync. So if it's negative, I'll just do my thing, but if it's positive, I'm going to skip to my exit. Recall that both halves of this PIA use the same vector handler location. So in theory, when my interrupt handler is called, it could be called because a horizontal sync interrupt came in. So this check verifies it's really for a field sync. That said, it's not strictly necessary because I did explicitly turn off horizontal sync. So this is really just maybe good practice, but it does waste a few cycles, so you could remove this if you wanted. The real work I'm doing is just incrementing a counter. That's all this handler is doing. And that leaves the cleanup. This is where I read the data register to reset bit 7 of the control register to 0 so that I don't keep on getting hammered. But what happens if I don't do this? I'm going to come back to that in a second. Let's just take a look at our main loop. I've got a couple counters. One is my main counter, and the other is the one you just saw for the interrupt handler. I clear them both. I initialize my interrupt, which you saw earlier. And then my main loop just increments the main counter over and over and over and over and over again. So the idea is that this should keep on going up, 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 and every time I get interrupted, this is going to go up. But let's see what happens when I fail to acknowledge the interrupt. Let's watch my handler get hammered. I'm going to set a breakpoint at the very beginning of my code here, and then another one on my interrupt handler right here. And let's take a look at these two counters at 3FOE and 3FOF. They're going to be right here and right here. We clear them. We initialize our interrupt. And I'm just going to go until we've gotten broken into our interrupt right here at 3F35. So you'll see after they got cleared, my main counter made its way up to hex 52. My interrupt counter hasn't gone anywhere yet. I'm going to continue. And I'm back in my interrupt, and that is going up, 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 up. And look at my main loop counter. It is starved out. I'm going to hold this down. Check this out. My main never gets control. My interrupt handler is just getting hammered and hammered and hammered and hammered because I never acknowledge the alarm clock. So now let's put it back the way it's supposed to be. And I still have my breakpoint set in the interrupt handler, so we're going to start by breaking there. And at that point, we'll see the main loop made its way up to BF. The interrupt handler is at 0. Go. Now that's up to 1. Still 8F. Oh, but oh, look at, oh yes. Oh yes. Each time this goes up by 1, but this goes up by a whole lot. So that means I got a lot of iterations in that main loop each time this has gone up. Well, I hope you found that interesting. If you'd like to learn more, I highly recommend, again, Nowhereman 999's blog. I have a link to that in the description where you can also find some code that my code was based on. Thanks for watching.